Hello everybody, welcome to today's lesson, and we're going to be talking a little bit about effects from soil liquefaction. Now in lessons 23, 24, and 25, we introduced the topic of soil liquefaction to you. We discussed looking at soil liquefaction susceptibility. We also discussed how we compute and analyze liquefaction initiation. But now we're going to be looking at liquefaction effects. And liquefaction effects are the most important aspect of liquefaction that engineers want to consider because it's the effects that are going to have the detrimental impacts on our infrastructure. This is a fun picture that I like to post as the intro on this slide. Look at this soil. It almost looks like the soil beneath these columns on this expressway here in Japan. It looks like they popped out of the ground, but that's not the case. From the 1995 Kobe earthquake in Japan, all of the soil around this expressway experienced settlement due to liquefaction, except right in these places where there is a pile cap beneath the ground surface supporting each of these big columns. So you can see how much settlement occurred from this earthquake. Today, we're interested in learning how to quantify two of arguably the most important effects to consider with liquefaction. The first being seismic compaction. This is settlement induced by liquefaction. Its technical term is seismic compaction, but a lot of people just refer it to post-liquefaction settlement. The next term is lateral spreading. This is the horizontal deformation of the soil due to liquefaction, and it occurs because of cyclic mobility liquefaction. So while, I'm not sure why that shrunk on me there. While seismic compaction deals with vertical displacements, lateral spreading deals with horizontal displacements. And both of these modes of displacement can be bad. So let's start with seismic compaction. Now, one of the most important or most common effects of liquefaction is settlement. So what happens is as the soil particles are trying to get closer and closer together, as they contract, they squeeze the water out of the pore space. And because of that, significant volumetric strains can occur in the soil. Now, technically, sand does not need to liquefy to experience these kinds of settlements. In fact, these kinds of settlements commonly occur in dry and even moist sands. So we can compute seismic compaction for both dry sands and also saturated sands. And here's my disclaimer. I have to say it because of my good friend, Professor Shide Dashti at the University of Colorado, who would already be reminding me that all of these methods of seismic compaction only deal with soils in the free field, meaning there are no buildings on top of them, meaning, so if I were to draw a sketch for you, it would look something like this. Here's the ground surface. Say I had a building sitting here with windows, and I had soil here, and say I had soil out here where there was nothing. Okay, if soil liquefies right there beneath that building, that is not the free field. But if soil liquefies here, where there are no overlying structures or embankments or dams or whatever you want to have on top of the soil, that is the free field. So why in the world do we even care about the free field? Because really we're only concerned about liquefaction and settlements beneath structures. Well, that's the dilemma. We don't have good data yet on settlement beneath structures. Now, the research is just starting to come out. I helped co-author a paper that's currently under review and hopefully will be published soon in Geotechnique on a model to predict strains and settlements beneath structures from liquefaction. But in this current lesson, everything we talk about is going to be for our free-filled conditions. So we will just treat these as potentially conservative settlement estimates. Okay, so first, let's look at dry sands. Seismic compaction in dry sands is something that can easily be computed using a method such as Tokimatsu and Seed, published in 1987. In this first step, we need to get the effective shear strain multiplied by the effective shear modulus divided by the maximum shear modulus for the site. So we need to do this for each non-saturated soil sublayer. Wait, non-saturated? Well, yeah, because we're looking at the dry sands, remember? So we're only going to look at the soil that's above the water table. So how do we get these values? Well, first of all, recall from our lesson on liquefaction initiation that the cyclic shear stress is simply equal to the effective shear strain times the effective shear modulus. And we can approximate that using the Seed-Idris simplified equation for cyclic shear strain given here. And remember that this R sub D is our depth reduction factor. From our liquefaction initiation method. So we get that from our liquefaction initiation calculations. Therefore, if I want to get this term here, all I have to do is take this and divide it by G max. And I'm done. So I get that as my input for the Tokimatsu and Seed method. Now this G max, this maximum shear strain, I can measure it from shear wave velocity methods, geophysical methods, or I can correlate it. It just depends. I mean, that's a topic in and of itself. Once I have the effective shear strain multiplied by G over G max, I compute the mean effective principal stress. Now, note, I'm saying mean effective principal stress. Why not just the effective stress? Well, because if I plot, let's change the color. I'm feeling daring today. We'll do black. If I have an element of soil and it's in 3 dimensions and it looks like this, the vertical stresses are going to act right there, and we'll call those sigma 1. But we know that there are also horizontal stresses acting on our soil element as well. We can call them sigma 2, and we can call them sigma 3. Now, we often just look at soil in terms of 2 dimensions, looking at it like this, where we say sigma 3 and sigma 1. Okay, we're not doing that anymore. We're looking at soil in its true sense in 3 dimensions. So if that's the case, then I need to account for sigma 2 and sigma 3. If I assume that sigma 3 equals sigma 2, then we also know that sigma 3 is equal to my horizontal earth pressure coefficient, or I'm sorry, not horizontal, we're going to say K naught, my lateral earth pressure coefficient at rest times sigma 1. Okay, well that's cool. So that means then that sigma 2 also equals K naught times sigma prime 1. So if that's the case, then if I just taking the average of sigma 1, sigma 2, and sigma 3, I get this relationship over here. So the mean effective principal stress is equal to this relationship. Now, if we don't know what our at-rest lateral earth pressure coefficient is, we can assume or treat it that it's going to be approximately equal to 0.5. And if that's the case, then we can get this relationship right here. 2/3 of our vertical effective stress. Once I have that, then I can move to step 3, where I'm going to obtain the effective strain from this curve. So here's my value of gamma effective times my G over G max that I computed in step 1. And I'm going to simply go up to my value. I'm going to pick the curve that corresponds to my mean effective principal stress, and notice that it's in units of tons per square foot. Not a set of units that we use very often anymore, but nonetheless in Tokimatsu and CEEN it is. And then we come up and come over, and we grab our effective shear strain, whatever that may be. Okay, that takes us to step 4. Maybe. There we go. Step 4, we are going to compute the cyclic shear strain, and that's going to be equal to the effective shear strain times 100%. So we need to use these charts down here below. So what we're going to do is we are going to find the volumetric strain from that cyclic shear strain for each unsaturated layer. So we can do it in terms of relative density, or we can do it in terms of standard penetration test blow counts corrected for atmospheric pressure. But note, not N160, where it's corrected for 60% hammer efficiency. Nope, it's just N1. So given my cyclic shear strain, given my N value, or my relative density, whatever I want to use, I come down for each soil layer and I go over and I get my volumetric strain for that layer that corresponds to the shaking. Now you'll notice here, this is going to contradict what I just said. If you know nothing about the hammer energy or those kinds of things, then you can go ahead and just assume or treat that N1 is approximately equal to your N160 clean sand. However, if you have enough information on the data, then go ahead and just compute your N1. Okay. Step 5, what we're going to do is multiply our shear strains from each unsaturated sublayer by 2. Why in the world would we do that? Well, because earthquakes shake the ground in 2 horizontal directions, not just 1. So a numerical researcher named Robert Pike discovered that, published it in a paper in 1975, and found that when you multiply these strains by a factor of 2, you get much closer to the realistic strains and settlements that happen in the soil. So once we multiply everything by 2, step 6, we are going to multiply our strains from each unsaturated sublayer by the strain correction factor to correct for earthquake duration. So this again has to do with the larger the magnitude, the longer the shaking is going to be. So this is going to be similar to our magnitude scaling factor. So here's a relationship that's recommended for Tokimatsu and CEEN. You see that it's a function of earthquake magnitude as long as your magnitude is between a 5.25 and an 8.5. Finally, in step 7, we're going to take our corrected strain and we're just going to multiply it by its corresponding sublayer thickness. And that'll give us the settlement for that particular sublayer. Now, if I repeat this process for every single sublayer and I sum those settlements together, I can get the settlement at the ground surface that results from seismic compaction of dry sands. So this method for dry sands is a graphical method. It's something that you cannot enter into a spreadsheet unless you digitize those curves, which a few people I know have done, but unfortunately I haven't done for you. Now let's talk about seismic compaction in saturated sands. And again, we're talking about free-filled liquefaction conditions. So if we're looking at settlements from post-liquefaction settlements in the free-filled in saturated sands, there are tons of methods out there. Lots of methods that have been published and that have been used by folks. Now, we're going to focus on just a couple of them, okay? Idris and Boulanger in their 2008 EERI monograph, and also later in their 2010 liquefaction report, recommend the use of the Ishihara and Yoshimine 1992 model with their liquefaction triggering model. So that's what we're going to talk about. Now, Ishihara and Yoshimine performed a whole series of laboratory cyclic shear tests, and they measured the amount of strain that occurred in their samples when they cyclically loaded them to different levels of loading, basically, and different levels of strain. And then they created curves or fit curves to the results that they observed. And here are the curves that they essentially observed. So you can see it's these curves are a function, again, of standard penetration test values. Now you're going to note again, oops, let's go back. These here are N172, which is not equal to N160. They're just slightly different. They have they're assuming a different hammer energy, or they're assuming a different efficiency in their hammers. And so N172 can be converted to an equivalent N160 by simply taking the ratio of 60 over 72. So if there's less hammer efficiency, say it's a 60% efficient hammer versus a 72, we know that it would take more blow counts. So we could just take this factor of F, and it's equal to 72 divided by 60. Thus, if I take N172 times 72 over 60, that should approximately give me N160. Okay. Now on the homework, if I just tell you to assume that N160 equals N172, then go for it. Otherwise, you can do this simple little correction and you'll be fine. Now, you'll see that it's a function of SPT resistance, which is a proxy for relative density, and it's also a function of the factor of safety against liquefaction. So remember, factor of safety against liquefaction is simply the cyclic resistance ratio divided by the cyclic stress ratio. You'll note what happens at a factor of safety of 1. At factors of safety less than 1, so up here this is factor of safety is, greater than 1.0, so we're not predicting liquefaction. Our strains generally are about 1% or less. So I mean, these are really small volumetric strains and settlements that are occurring in the soil. But look what happens at factors of safety that are less than 1. We can get strains all the way up to 5.5% in some cases, and so we can get some massive strains and settlements. So here's the procedure that Idris and Boulanger recommend. And again, we're going to be using N160 clean sand from the Idris and Boulanger approach and their computed factor of safety to approximate these Ishihara and Yoshimine values. So what we can do is first, Ishihara and Yoshimine presented this equation as a function of N160. That's right, this is N160. No need to convert to N172. Whoops. Because that's already been accounted for in this relationship, okay? So with that conversion, this is basically the numerical version, or the equation version of this plot right here. And so we thank Professors Shear and Yoshimine for providing that for us. Now, Idris and Boulanger said we need to get a couple of parameters for us to be able to estimate this maximum shear strain from the soil. So the first thing we need to get is a factor of safety parameter that they call factor of safety alpha, or just F sub alpha, and it's equal to this equation right here. Then we also need to get the limiting shear strain of the soil, which is basically the shear strain that we do not think the soil is ever going to surpass. Oops, I've got some stuff in your way there. I apologize. There we go. Oops, went too far. Next, if our factor of safety for a soil layer is greater than or equal to 2, then we're going to say that the maximum shear strain is equal to 0, and thus the volumetric strain is also equal to 0. If our factor of safety is between 2 and our reference factor of safety, F sub alpha, then we're going to use this relationship right here to get our maximum shear strain. So it's just an interpolation. If our factor of safety is less than our reference factor of safety value, or our F sub alpha, then the maximum shear strain is equal to our limiting shear strain. So you can see where your spreadsheet is going to have basically some conditional or maybe some if functions in there. So that's it, by the way. I mean, that's how we get our, again, the whole reason we're doing these equations is to get the volumetric strain for some soil sublayer. Okay. Now moving forward, Professor Onder Chetan and some of his colleagues in 2009 published an interesting paper. And they asked a really pertinent question, which is, how well do these methods of computing post-liquefaction free-field settlements work with actual settlement case histories from the field? So they went and they gathered around 40 case histories or so, post-liquefaction case histories, and they evaluated numerous models, including the Ishihara and Yoshimine model, against those actual case histories from the field. And there's something that they observed. Some models had a positive bias, meaning they tended to overpredict the settlements. Other models tended to have a negative bias, or they tend to underpredict the settlements. So Chetan and others developed a correction scheme to try to correct these different settlement models and calibrate them for actual field or field observed liquefaction settlement case histories. So here's their approach. First of all, they compute an equivalent strain for the entire susceptible soil layer at depths less than 18 meters. So what does this mean? Well, I'm not going to rate that right now. What this means is, say that I have a soil profile and it's divided into a whole bunch of different layers, and I get strain from, let's see, I have 1, 2, 3, I've got 4 layers there, so that's strain from layer 4, here's strain from layer 3, here's strain from layer 2, and strain from layer 1. What they are proposing to do is to convert that, oh, that's an awful looking arrow, I'm so sorry, to an equivalent strain for one single layer. So in other words, we're going to treat all susceptible soil layers at depths less than or equal to 18 meters below the ground surface as one equivalent soil layer. So we're only going to have one calculation, basically. That's the Chetin and others approach. So we need to compute that equivalent shear strain, and it's going to be a function, of course, of the individual layer strain weighted by the layer thickness T. But you're going to see this other term here called the depth factor. This is a depth weighting factor that accounts for the well-known fact that soils that are deeper tend to have a minimal impact on settlements observed from the ground surface. But the closer that soil layer is to the ground surface, the more likely that its strains will propagate to the ground surface and will cause a noticeable settlement at the surface. So they did some numerical studies and found that a depth of about 18 meters is the cutoff depth. If strains occur below depths of 18 meters, the soil is likely going to bridge as the strains propagate to the ground surface. That means that you're probably not going to see those settlements on the ground surface. However, if strains occur at depths less than 18 meters, then there's a chance you will see those strains all the way at the ground surface. So this depth weighting factor is Chetin and others' way of accounting for the fact that the more shallow the soil is, the more likely you're going to see its impacts on the ground surface. And then once you get your equivalent strain, all you need to do is multiply it by the summation of the thicknesses of all of your susceptible soil layers at depths less than 18 meters. At depths greater than 18 meters, don't even worry about them. Don't even look at them. You don't need to care for a post-liquefaction settlement. Now they also threw in the 0.9 factor, which is basically just a fudge factor to correct the Ishihara and Yoshimine calculation for the bias that they observed against the actual case history data that they studied. And then they were also to observe that the standard deviation in computing the surface settlement was approximately 1.12 in logarithmic units. That's huge. That's like a factor of 3 or 4, basically, which tells us that these methods aren't the best, but they're the best that we have currently. Okay, so that's enough about seismic compaction. Let's talk about lateral spread. Now, lateral spread is one of the most damaging hazards associated with a liquefaction. It doesn't kill people. Lateral spread can be pretty slow moving, so it's not like it's burying anybody. But it does pose a tremendous risk to things like bridges, to things like ports, to things like roads, railways, lifelines, buildings, airports, I mean, you name it. Anything that could be damaged by lateral movement of the soil, lateral spread poses a risk. Lateral spread works like this. So here's a cross-section of a bridge crossing some body of water, and you can see that I have dense sand, I have loose sand, I have piles that are supporting the bridge, I have a non-liquefiable clay crust, and then I also have maybe some compacted embankment fill for my road as it approaches the bridge. Now, an earthquake might occur, and if the earthquake occurs, it's probably going to saturate, or it's probably going to liquefy my saturated loose sand. If that occurs, then there tends to be some downward slope movement towards the river channel or the body of water. And even if you don't have an open face and the ground is just sloping, gravity can still pull all of the ground downslope. So we get these downslope movements during the course of the earthquake while the soil is liquefied. That will result in something looking like this, where the overlying soils slammed into our bridge on our bridge foundations. We get bending of the piles, breaking of the piles. We get compaction and potential damage of our bridge. We get cracking in the soil. We can have even sand boils on the ground surface. It can be really, really messy. And, to case in point, here's a really good example from a highway bridge up in Anchorage, Alaska. And it shows exactly what happened after the 1964 event. So there's two general approaches that engineers can use to compute lateral spreads, and the first is called the first are analytical methods. So these are methods where we might treat the soil like a sliding block. We'll learn more about these in a later lesson, but for instance, like a Newmark sliding block, or they might involve like a finite element analysis. So I know my friend Professor Ross Boulanger and his colleague and former student Katerina Ziatopoulou have been doing this type of analysis with their constitutive model PM4 sand in the finite difference software FLAC. And there's other solutions out there. Now these tend to be pretty complex and hard to do, but more and more we're seeing promise from these analytical methods. And so, I predict in the future that more people will be using these and relying on these methods. So I am a fan. The problem is they're not very practical today. The second approach involves empirical data. So with empirical data, we're not interested in trying to explain the phenomenon. All we're interested in is observing and using statistical regression to fit some mathematical function to the data that minimizes the error. So it's not based on physics at all, but they are easy to perform, but they can be dangerous if we extrapolate with them. If we use the models appropriately, where the data that we're putting into the model is appropriate and within the bounds set by the database, then empirical methods can be great. So arguably the most widely used and popular empirical method still in use today was originally published by Professor Stephen Bartlett and Professor Leslie Yau in 1995. This is known as the Bartlett and Yau Model. Now, the Bartlett and Yau Model considers two possible cases of lateral spread. It considers a ground slope case. So in a ground slope case, this would look something like this, where we have sloping ground and we have a liquefiable layer, and we expect to see lateral movement downslope. So this would be a ground slope case. The other case would be a free face case. And a free face case is where we might have like some open channel, like it could be a river, it could be a canal, it could be the ocean, it could be whatever, and say that we have some liquefiable layer down here, and we can get horizontal displacement towards our free face as the earthquake shaking attempts to level the ground. So these are the two cases that they divided their empirical database up into. Now, here's one of the tricky things, right? Your site can be either a ground slope case or a free face case. In the Bartlett and Yau model, there is no combined approach. It's one or the other. So my recommendation is, if you have a combined case where you have a slope in your soil and you're next to a free face, you should analyze both the ground slope and the free face cases and pick the one that gives you the most conservative model. Now, for the free face case, if we are characterizing site geometry, Bartlett and Yau used two parameters. The height of your soil, so say here's your site, here's your canal or river channel or whatever. H is the height from your site to the toe of your free face, whatever it is, and L is the horizontal distance from the toe to your site. What we do is we compute the free face ratio, and it's simply the ratio of the height to the length in percent. So it's not a decimal, we multiply it by 100 and give it in terms of a percent. So here it is in all its beauty and glory, the Bartlett and Yau model. It was updated in 2002. A bunch of data points were added, a bunch of other data points were taken away, and in total they had, in their 2002 update, around, I want to say 480 or so case histories in their database, the majority of those coming from the 1964 Niigata earthquake. But here is the model as we can see, and there's a couple of things I want to point out to you. So R, this is the source to site distance, and a lot of confusion has been had about R and R star. So these are distance terms. R is essentially equal to RJB, folks. So you guys are familiar with computing ground motions from attenuation relationships. The R in the Bartlett and Yau relationship is the same as RJB, which means that if the rupture plane of the fault is beneath your feet, even if it's deep, then your R is effectively 0. It's the horizontal distance from your site to the rupture surface, or the projection of the rupture surface. I'll give you an equation to compute R star in just a moment. And then, it keeps going to that page. Let me go back. W is our free face ratio. S is your ground slope, if you have a ground slope case, so it's the gradient of the slope in percent. T15 is an interesting parameter, okay? T15 is the cumulative thickness of your saturated granular or silt layers where the N160 values of those layers are less than 15 blows per foot. So what does this mean? This means if I draw a soil profile and I have all sorts of layers in here, and let's say in this particular case that thickness is 5 meters, and let's say that thickness is 1 meter, and that thickness is 3 meters, and that thickness is, I don't know, 4 meters, and that thickness is 3 meters, and that thickness is 1 meter. And let's say here that N160 is 10, and let's say that N160 here is 3, so it's really low, and let's say N160 is 5, N160 in this layer is 19, N160 is 12, and N160 is 20. Let's say that groundwater is right at this depth, and let's say that this is sand, this is clay, this is sand, this is sand, this is clay, and this is sand. So here's just the potential soil profile you might encounter. So what contributes to T15? Okay, so it's going to be my saturated cohesionless soil layers. And it's going to be those layers with N160 less than 15 hammer blows per foot. Okay? So what about this layer? Nope, not going to happen. Why? Because it's above the water table. It's not saturated. So what about our clay layer? Is that going to work? Nope, because it's not cohesionless, folks. It has to be cohesionless. What about this sand layer? Well, it's sand. It's below the water table, and the N160 is less than 5. So, yep, that's going to count. What about this layer here, this sand? Well, it is below the water table, and it is a sand, but the SPT resistance, the blow count, is greater than 15. So, nope, not going to count that. What about this clay right here? Nope. Whoops. I'm getting ahead of myself. Nope, not going to count it because it's a clay. And what about this sand right here? We're below the water table. It's sand, but the SPT resistance is above 15. So nope, we're not going to count that. So for this soil profile, the only layer that contributes would be this one layer, and we would say T15 equals 5 meters. So let's just change this and say, what if that bottom layer was maybe 9, not 20? So if that was the case, it was less than 15, it's saturated, we would say, yes, it counts. So we would add its thickness to T15. It would therefore, T15 would be equal to 6 meters. Okay? F15 is the average fines content in those layers that made up the T15 value. So we're just going to take the thickness weighted average of the mean fine, so the mean fine content of those layers that contributed T15, and D50, 15 is the mean grain size, so the 50th percentile from our sieve curves that we get from a particle distribution analysis from those soil layers that make up the T15 parameter. Now, a couple things I want to point out here. Even though this is an empirical equation, the reason that this equation is still kicking, even more than 20 years later, is that it still captures the fundamental processes that contribute and govern the phenomenon of lateral spread. Look, for instance, I've got these terms right here, which contribute my seismic loading. So they quantify how much intensity, in essence, is going into my lateral spread problem. Okay? Then I've got these terms right here. And these are quantifying the site geometry, which is contributing to lateral spread. If I didn't have slopes, if I didn't have open channels, I wouldn't have a lateral spread problem. And then I have these terms right here, which are quantifying my geotechnical properties. And because of those terms are basically identifying the soil layers that I've been shown to correlate and statistically govern the behavior and the quantity of lateral spread displacement that occurs. So this equation, even though it is empirical, it is statistical, it still captures the important contributions of seismic loading, site geometry, and geotechnical properties. Now we can finally move forward to this slide. All of these B values here are just regression coefficients that are given in this table shown right here. So depending on whether you have a ground slope case or a free face case, you just plug in your different coefficient values. And here's the equation to compute R star. This is an equation that attempts to prevent the model from blowing up from near field events. So you can see it's just a function of your moment magnitude. And the scatter of the data. This is the logarithmic standard deviation of 0.197. Let's see if we can change the page here. When I want to change the page, it won't. And when I don't want to, it will. Okay. Remember, this is an empirical equation. So that means that extrapolation is bad. We don't want that. As much as possible, we want to avoid it. So here are the ranges that Bartlett and Yau said for the different input parameters that are valid to be used with their model. So you may want to check that and make sure that the values that you're inputting into the equation work. Also, in terms of fines content and mean grain size, here are all the values from their case histories. So you see that they bunch together and they form or coagulate this nice little area here, that as long as your points fall within that bound, you're okay. You can feel confident. If your point falls out here or up here or something like that, then you're probably extrapolating with the model. So this is a fun plot I always like to show because I call this the reality check plot. So if I take the data from the Bartlett and Yau database from which the model was regressed, and I just plot the actual displacement from the case history versus the predicted displacement from our model, this is what we get. And honestly, it looks kind of like Grandma went crazy with the shotgun again. This line would be a perfect fit. And you see that we tend to scatter about the line, generally within a range of 1/2 to 2 times the predicted value. So essentially what they found was that 95% of the data fell within a factor of 2 of your predicted displacement. Now that might be disappointing to many of you who like a lot of precision and accuracy, but bear in mind that lateral spread and soil liquefaction in general are very, very, very complex and complicated phenomena that are difficult to just wrap simple equations around. So the fact that this model got within a factor of 2 of 95% of their data is pretty remarkable. So that's the end of our lesson today. Bear in mind and remember that these two effects, seismic compaction and lateral spread, are the two most common effects associated with liquefaction and are going to be the two that probably govern the response of the engineer to liquefaction more often than not. So go ahead and let me know if you have any questions, and good luck on your homework assignment next week, guys. And I will see you when I get back. Have a great day.